Now we are going to briefly review signal-to-noise ratio requirements in this 3G system before going into a deeper analysis of the link budget. In digital system, the main parameter is the energy per bit to noise power spectral density. Sometimes it has different names, but this is the way to define it. And maybe sometimes you will hear the word digital SNR, different names maybe would be used, but the normal representation is the bit energy and the noise power spectral density, and not an EV. And this really depends on two things: the power in the carrier frequency, the carrier wave, and the time duration of one bit. So if you multiply the power, which is the number of watts per second, by the time duration of one bit, you get the energy associated to that bit. And the noise power spectral density is also the energy associated with noise. You could write this time as an inverse, and this will give you the data rate. This is the number of bits you can send per second. Now, in 3G phones, we use binary phase shift keying, and those pulses are shaped using a raised cosine filtering. And at the end, it comes out that the bandwidth, for this case, is equal to the inverse of the pulse duration. That means that the bandwidth is equal to the bit rate. So you can equate this with the bandwidth. In this particular case, if there is a different modulation, things would be different. But for EPSK, this is the value. And we could rewrite this in this way. This is the bit energy. That's the same expression we had before, up until here. And now, since this is what happens in this case, we substitute this by the bandwidth, and so we end with the carrier to noise or signal to noise ratio. So for this particular case, the signal to noise ratio in the classical analog system is exactly the same number that will give you the signal to noise ratio in the digital case. This is something to remember for this particular modulation. But this is not the only type of code we can use. For instance, before we commented on QAM, quaternary codes, for instance, block is just a block of two bits, and we assign one symbol to each one of them. For instance, it could be 4 amplitude levels. And you could generalize this to MRI codes, where you take blocks of M messages and you represent them by a waveform, if you want, by a letter of an alphabet, that is related by a power of 2. For example, in a 16 QAM scheme, we use 16 symbols, and we could represent 4 bits per symbol. We are going to see some examples later. Now, since now each symbol corresponds to this number of bits, log 2 of the alphabet length, then the signaling rate, which is really the number of symbols we send per second, which this is called from the old telegraph times a baud, then we have decreased this number, because in fact this is the signaling rate, this is the bit rate, and this is the M we have here. For this scheme will be 4. So that means that now we can send many more bits over the same bandwidth, but you have to pay a price. Things are never easy, and you have to pay prices. So what's the price here? Well, you can observe simply in an amplitude modulation scheme like this one, that now we have 4 amplitude levels. To separate them, we need to have a much larger amplitude margin. So in this case, we can send more bits through the same channel, but we have to pay this with a signal to noise ratio, which is not as good as the one you had before. So you are trading data rate for signal to noise ratio, and you have to play with them. One of the main parameters to consider in digital communication systems is the limit that was imposed by Shannon's theory or by Shannon's formulas. And this is the basic Shannon law that tells you for a certain bandwidth and a signal-to-noise ratio, it gives you the maximum capacity, if you want the maximum data rate, that you can send with an arbitrary or controlled number of errors, a small number of errors. So the capacity is in bits per second, the bandwidth is in hertz, and here you take log 2, because those are bits, and 1 plus the signal-to-noise ratio. So you can increase the data rate, which is C in this case, in two ways. One is just to increase the bandwidth, and the other way is to increase the signal-to-noise ratio. Okay? So those are the two things you can do. So let's assume that we increase the bandwidth. We have a fixed signal-to-noise ratio, and now we are going to see the effects that it's going to have on the data rate if we just increase the bandwidth. So formally, what we do is we write here a limit when the bandwidth increases largely for the capacity. We have to take this limit, and the first thing we do is we just change this log base 2 to Neperian logarithms, and we have to divide by Neperian log of 2, and everything else is the same. And this is simple because if we increase b, that means that this term becomes smaller and smaller, so you can approximate this by this number. So now we have here this product, this times this. So at the end, what we have is the signal divided by the noise power spectral density and divided by Neperian log of 2. That's what you have. Now, if you write the limit of the energy per bit to noise power spectral density, this is the same thing as saying, well, the energy per bit is the power divided by the bit rate and then not. But the bit rate was here too. So this number is equal to what you have in this formula except for the log of 2. So the limit of the bit energy per noise, the signal-to-noise ratio in the digital case, is going to be log Neperian of 2, which is, this is minus 1.6 dBs. And you cannot do better than this. So this is just the limit that is set by Shannon's, and this is known as the Shannon limit. So this is the minimum requirement if you are free to increase a lot the bandwidth. This is what we do in 3G phones, all right? They work well with low signal-to-noise ratios, but the price to pay is that they require a very large bandwidth. We are going to comment on how this is achieved. There are different techniques to increase the bandwidth, and they've been in use in different scenarios. One is just to make the carrier frequency shift along a certain pattern. Just keep changing the frequency, and this is why it's called frequency hopping. You just keep doing this. There's another way in which you just now change not the frequency but the time slot. So you are just transmitting through different time slots that you know the sequence. Then there's another one in which you take your bits and you combine them with another sequence, which is just a very large number of bits. This is called direct sequence. And this is the one that is being used in 3G phones. So you take your data bits and then you multiply them by a large set of random bits. And to distinguish them from the, let's say, from the important bits, the ones we generate, we call those code bits chips. So whenever you hear a chip, that meaning is a bit in that sequence that is spreading your signal. And then there are other ways of doing this by multi-carrier, but we are going to comment on this case, the direct sequence spreading. How this is done, here you have a simple example. And the first thing you have to do is you have to generate a sequence that will multiply your original bits. And this is a code tree. This is the way to generate a code. We start with 1 bit. Here we have 1, 1, 1 minus 1. Now we have already 2 branches. Now, once again, we go to the following branch. And here we have 2 1s and 2 1s. And here 2 plus and 2 minus. And this is the one we're going to take into the example. When you take this one, you repeat it. You have this branch. And this, all those, and then you keep going on. And the number of bits here is called the spreading factor. And those sequences are denoted as orthogonal variable spreading factor sequences. And they have an interesting property. Is if you follow one of those branches, it will be orthogonal to any other. So as long as you do not repeat the branch, then you can select different sequences. Now, this is applied in the following way. You have here a simple binary sequence. Plus 1 is 1, minus 1 is 0. And let's assume the length of the pulse is 100 microseconds. And this is your data. That's the data that the user has to send. And here we have a code. And we select this code. This code goes 1, 1. And then minus 1 is a 0. So the sequence here, and it has 4 bits, 4 chips, if you want, for every bit in this signal. And now we repeat, we keep repeating this, and we multiply. So we start here, and we have plus 1 and minus 1. This gives a 0. Plus 1, minus 1, 0. Here we have minus 1, 1, another 1, another 1, and then we go to 0. So now this sequence has been spread, has been expanded to this larger sequence. Again, it's a non-return to 0, but this is just the basic parameter. But we have now changed data rate. The data rate for the code now is 4 times the original data rate of the user bits. And that's the way this thing proceeds. And this is done in a simple way in those phones. What they do is they enter the data, the spreading sequence, and they multiply digitally. So at the end here, the data rate is increased. And with this, you modulate the BPSK signal, and you just send the signal. And on reception, you do the inverse. You use the same sequence, it has to be known, and then you de-spread and you go through this process. This is the way to go. The codes in this cell phones they are really complicated and could be very, very long. And in fact, there are 2 codes involved. One is the spreading, the one that takes your bits and make just a much longer sequence. And the other one is the scrambling that mixes in a random way, but known way, those bits. All right? So the first family of codes is called channelization codes. And they are a family of codes like the one you saw before. And the length of the code could go from 4 to 256 chips in the uplink and double in the downlink. And they are used in the uplink to separate different data. Could be your speech, your data, other things you are doing or the phone is doing. So this is one way of separating different uses. On the downlink, they are also separating different sectors, different cells, and this is just a different number, but that's the basic. Now, the scrambling is just using pseudo-random sequence. They resemble noise just to make things even in a frame which is 10 milliseconds, and this is just the definition for this. And the number of codes is really on the uplink, on the terminal, is 2 to the 24. It's just immense. And the downlink is only 512. It's 1 per sector or cell. So here it identifies the cell, the base station, but this is different in one case than the other. And you have to combine those 2. So you enter your data rate, and then here this is a much higher bit rate, and this is the signaling rate. And how this is done, combined with the modulation, well, here you have a simple example for the downlink. This is the data rate. It's separated in a serial parallel converter, and here you get, for instance, the even bits, and here the odd bits. That means that here the data rate is half of the original one, okay? And they enter. Yes. Now here you apply the channelization code. You apply also an orthogonal. In this case, it's just a complex. So at the end, you get a complex representation of the two families of bits. And then you apply the scrambling complex code. You could in some way go from here to here. And now you have to separate the real and the imaginary part. And with this, you modulate a cosine and a sine subcarrier that are orthogonal. You mix them, and this is your, in this case, this is your signal. This is the signal that you send through the channel. And this is for most of the downlink channels, except for the synchronization one. In the uplink, it's a little bit different, but the principle and the idea is the same. So we really play with the bits, with the data bits, and we just spread them in such a way that they are going to occupy a much larger bandwidth. In this process, we have a gain. We get a gain, and the gain is just the spreading factor. For instance, for the speech connection, which originally was 12.2 kilobits per second, and the chip, the spreading sequence, brings this to 3.84 megachips, then 10 log of this ratio gives you a gain, a processing gain of 25 dBs. So this is really the main advantage of CDMA systems. If the data connection is at 144 kilobits, then the gain is lower, but it still is significant.